Okay, hey, we're so this is now chapter 15. In particular, we're looking at vector fields. And vector fields are, they're pretty awesome. They're a lot like slope fields that you saw back when you were working with differential equations in Calc 2. They're awesome because you can model all kinds of physical situations, like you can model airflow. If you're looking on the right at figure 15.2, you could model sort of the velocity of all the particles on a rotating wheel. As you get closer to the middle, your velocity is getting smaller and smaller. So the little arrows indicate kind of how big the velocity is and the direction. Gravitational force, you can model that. If you're a flat earther, you don't believe in gravitational force. All kinds of good stuff, right? So it's just an awesome thing. We begin with just sketching these guys, and they'll go through and talk about certain types of vector fields, like the gravitational field, in particular inverse square fields, which all have this common characteristic that we'll talk about here in a bit. But let's just work with sketching first. So part A, sketching, and look at example 1. So it works the same way as what you did in Calc 2 with regards to slope fields. So here we have negative y comma x, and you could basically do like a table, x, y, and then your, negative y comma x, like this, if you wish. And then pick some points, probably around 0, 0. So negative 1, negative 1. Negative 1, 0, negative 1, 1. So I'm just going to pick like 9 points around the center. 0, negative 1, 0, 0, 0, 1. And then I'm going to have to smush those vectors in there. 1, negative 1, 1, 0, and 1, 1. So the vectors, hopefully I don't screw them up. 1, negative 1. 0, negative 1, negative 1, negative 1, 1, 0, 0, 0, negative 1, 0, 1, 1, 0, 1, and then negative 1, 1. Okay. And so at all those points in the xy plane, you're just going to attach those vectors, and that's it. Okay. Clearly, you don't want to do this by hand to any extent, even though I was forced to do this when I went to school. Hey, let's sit around and fill a notebook full of these things, So, thank you for the education, right? But anyways, let's plot those vectors. So up 1, I keep getting my left and right confused, my up and down. So right 1 and then down 1. So the first vector is kind of pointing downwards. So right 1 and then down 1. So it's going to go like this. The next one, 0, so don't move, down 1. And this guy here, left 1, down 1. So it looks like that. Moving on to the next set, I guess at 0, negative 1, we have go right 1 and then 0. At 0, 0, we have 0, 0, so it's just a point. At 0, 1, I have back negative 1 and then 0. At 1, negative 1, I have right 1, up 1, so it'll look like that. At 1, 0, I have don't move and then go up 1. And then at 1, 1, I have left 1, up 1, like this. So you get kind of this rotational type looking picture. The book does more points, and they give you this. And you can kind of see it's kind of like a circular figure. And so you could think of this as like a wheel rotating and at any point giving you the velocity. Okay. So in the actual homework, what they'll do is kind of give you multiple choices, and you just have to kind of maybe plot 1 or 2. So like problem 1, which I apparently got wrong. F of x comma y equals I is y and then 0, right? So again, you could just test a couple. I mean, you don't have to draw it. You can kind of just fiddle around and figure it out. But you know, at 0, 0, it'll be 0, 0. At any y coordinate of 0, so like 0, 1, you're just going to get 0, 0 vector. So it will likely be, you know, well, let's see, f of 0, 2. Well, I screwed that up. Oh, geez. I'm having all kinds of troubles today. This would be 1, 0, so sorry. At 0, 1, I would have over 1, don't move. At 0, 2, it's bigger, right? So then it would go over more. At 0, 0, there's like nothing there. At negative 1, so this one would be 2, 0. F of 0, negative 1 would be negative 1, 0. So it's going now in the other direction. And so it's either the one of the bottom two. You know, it's clearly one of those. Then you could just go out a little bit, like to I don't know, 1, 2, 1. So f of 2 comma 1 is going to be 1 comma 0 again. So it's going to be going like that again. So it looks like it's I screwed that one up. Yeah. So it's that guy. Let's see if it's right. Yeah, so you just do some test values and do process elimination, and yeah. Okay, so the common characteristic of like some of these special gravitational fields is that they are what they call conservative. And it's conservative if there exists this function out there such when you take the gradient of it, you get the vector field. Okay. So here, you know, it's noting every inverse square field is conservative. Tests for conservative vector fields, basically what you're doing is comparing the mixed partials. So let's make this kind of a new section, right? So this is section 2, conservative vector fields. So a field, a vector field, F is conservative, sorry about my writing today, when there's a function f, little f, such that the gradient of that thing is equal to this big F. Okay, so there exists some function on the mountaintop such that when you take its gradient, you get the vector field. And that super function on the mountaintop is called the potential function, which I probably won't call it that, but I'll just call it little f. So you're going to have to be able to find these things eventually. Like I said, if you're just given the vector field, you can do this test for conservative to see if it's conservative. So I guess theorem 15.1, if you have so if you're given this vector field m comma n, then it is conservative if and only if the partial of n with respect to x is equal to the partial of m with respect to y. And all this is saying that the mixed partials are equal, which is something you kind of learned earlier, given some nice characteristics of the derivatives, right? So so again, big F is conservative if, so note, big F is conservative if it was the gradient of some little function f. In other words, the gradient, if you remember, is just the partial derivative of f with respect to x, comma the partial derivative of f with respect to y. This guy right here is your m. This guy right here is your n. So if you think about it, so notice then also the partial derivative of m with respect to y is fxy, right? The partial derivative of n with respect to x is going to be fyx. And then we know that those things are equal, so that becomes kind of our test, right? To see if there was this function that kind of generates the vector field when you take its gradient. Yeah, okay, so with regards to the exercises here, they seem to be pretty simple at first. So for number 4, find the conservative vector field for the potential function by finding its gradient. So here all you're doing is getting a gradient, and then you know your vector field is conservative. Okay, so 9x, y, z. So the gradient of f, which will be our vector field, will be first with respect to x, so 9yz, and then with respect to y you get 9xz, and then with respect to z you get 9xy. Okay, and there you go. That thing's going to be conservative. The test for space vectors like this guy, for it to be conservative, you have to do this kind of cross product operation we'll look at called the curl in this section, but we're not there yet. Okay. Number 5, then you're kind of given now a vector field and you have to determine if it's conservative. So our vector field is 7y to the 9th, comma 63xy to the 8th, right? Whoops, need my little thingamajig here. Okay, so to test to see if it's conservative, you look at the mixed partials, right? So you're presuming that this is the partial derivative with respect to x, so you want to take the partial derivative of that thing, which we're calling big M, with respect to y. Okay, so that derivative there with respect to y will be 63y to the 8th. Then this other guy we assumed is a partial derivative with respect to y of n, so we want to now take the derivative of this thing with respect to x, right? So that derivative then is 63y to the 8th. Those things are equal, so the mixed partials are equal, so therefore this thing is conservative. Okay, so therefore conservative. Okay, so another one, this one's just more complicated, you know, determine if, do you know how to take a derivative with respect to x and with respect to y? That's basically all it's asking. We can look at it. So I have y all over 1 plus xy to the 1/2, comma x all over the square root of 1 plus xy. Same thing, or parentheses to the 1/2. Now I have to do all right, so the first guy, again, that's supposedly the derivative of something with respect to x, so we want to take its derivative with respect to y. Okay, and again, we're calling that m. And this guy over here, supposedly that was a derivative of something with respect to y, so we want to take its derivative with respect to x. Okay, so this guy, with respect to y, I'm going to have to go low d high minus high d low, so low 1 plus xy to the 1/2. The derivative of high is 1 minus high times the derivative of low. So I'm going to have to bring down the power rule, 1/2, 1 plus xy, now to the negative 1/2, times the derivative of the guts, that's the chain rule, with respect to y, that will be x. Okay, all over the bottom squared, so 1 plus xy to the 1/2 squared will just give you 1 plus xy. This thing, I'm going to multiply top and bottom by something special to make everything real nice like. And guess what? I'm going to multiply by 2 and then 1 plus xy to the 1/2. Okay, And if you do that in the top, you have to do that in the bottom. So 1 plus xy to the 1/2, lost my x. Okay, so distributing this in the first multiplication, the exponents will add together to give you 1. So I'll have 2 times 1 plus xy. In the second multiplication, the 1 plus xy and negative 1/2 times 1 plus xy to the 1/2, add the exponents, you get 0. So that part will go away. 2 times 1/2 is 1, and you'll just have minus xy. Okay, all over 2 times 1 plus xy to the 2 halves plus 1/2 is 3 halves. And of course, that will be 2 minus, or rather plus, I guess 1xy all over 2 times 1 plus xy to the 3 halves. Okay, grand. All right, what about the other derivative? That's pretty much the same thing, except instead of a y in the numerator, you have an x, and you're taking the derivative with respect to x. So again, you're going to end up having to do kind of a product rule on this. Let me see if I can smoosh it in right here. So I'll have 1 plus xy, or a quotient rule, not a product rule, to the 1/2 minus x times the derivative of the denominator, which would be 1/2 times 1 plus xy to the negative 1/2 times the derivative of this with respect now to x, which will be y, and then all over top of 1 plus xy to the 1/2 squared. So it's just 1 plus xy. Compare and contrast these things, they're exactly the same, aren't they? Right? The only difference is that these guys are swapped. The x and the y get swapped. Other than that, they're exactly the same. So we'll say that, yes, these are equal, and therefore it is, guess what? Conservative. Okay. Yay. Okay, so that will entail all kinds of neat stuff that we'll explore. They're going to have curl and divergence of vector fields. So these are operations that we'll need in order to make some kind of translation formulas later. So we'll be able to move from like single integrals to double integrals, and double integrals to triple integrals, and we'll need this kind of vocabulary. So let me look where we are in the book here. Do I need to find anything? Oh, we didn't do finding potential functions. So this is kind of a skill of into itself. So section 3. It's a little bit complicated the way they lay it out. So what I'm going to do is kind of just give you a formula for it. This is generally what I do in my differential equations class. When you have a space, a vector field in space is a little more complicated, but for these kind you could just kind of use a given formula. So anyways, section 3, finding the potential function. So you have to presume that the vector field is conservative. Okay, so the vector field must be conservative. Okay, so generally you have to check that first. But anyways, let's look at an example. Well, let me give you the formula. Okay, so first, this is kind of the two-dimensional version. The formula will be the partial with respect to y of the integral of m dx, and you'll set that equal to n. So that may look kind of mystical. Why is that? Well, if you think about the vector field, and it equals sum m comma n, we're saying that this thing is the result of taking partial derivatives of some potential function f, right? If you go in this way, it's the partial with respect to x. Go this way, it's the partial with respect to y. Okay, so what that formula does is first it'll take m and then integrate it back up to f with respect to x, right? And it'll give you a formula, but there's going to be unknowns in that formula, because when you took the derivative with respect to x, you may have inadvertently kind of completely destroyed some function in terms of y. It's kind of like the constant of integration. You don't know what it is, you know. So there's kind of this unknown part. So to remedy the fact that you have some unknown stuff, what you do is just take that and take its derivative with respect to y and set it equal to n. And doing that, you'll be able to solve out for the unknown part. Okay. And that's basically what they're doing in the book. It's just, I like this formula better. I think it's a little more straightforward rather than kind of just throwing a bunch of stuff at a wall and seeing what sticks, right? The 3D version is more like just throwing a bunch of stuff at the wall and seeing what sticks. I don't have a nice formula for the 3D version, but fortunately for all the ones I've seen in the homework, they're pretty easy. And I think there may only be one in the homework where it's three-dimensional. But let's take a look. I don't think I even put one in the homework for finding the... yeah, so there's not even one in here. I think maybe there's some in 15.2 or something. So it becomes an issue later, so I do need to deal with it. So yeah, let's do example 6. And we're going to employ this formula. And truthfully, you can go in either direction. You could also take the integral of n with respect to y, take its partial derivative with respect to x and set it equal to m. Okay, you could do that too. It'll work. But let's just use the way I've set it up. Okay, so their vector field is going to be 2xy and then x squared minus y. Okay. You do this in differential equations, so if you took differential equations, you've already seen this. But anyways, here we go. Partial with respect to y of the integral of 2xy dx, and we want to set that equal to x squared minus y. Okay. All right, so first I'm going to integrate 2xy with respect to x. And what do you get? Well, you get x squared over 2x squared over 2, so x squared and then y, and then plus this thing that may have been kind of annihilated when you took the derivative with respect to x. Okay, so it's some function of y that we're kind of worried about. What you have there is the solution. This thing right here is f. Okay, the only problem with it, again, it has that unknown function g of y. Okay, so to alleviate that issue, what I do is then just take the derivative with respect to y and set it equal to n. Right. So okay, the derivative of that thing with respect to y is going to be x squared plus g prime of y, and that will equal x squared minus y. Okay, now you have basically a differential equation. Move the x's to one or the other side, they'll be 0, they'll go away. You have g prime of y equals negative y, and then you can finish off the problem by integrating both sides with respect to y. Okay, so you'll end up with g of y equals negative y squared over 2 plus some constant, but the constant for us really isn't going to matter. But at the end of the day, what you'll do then is just plop this expression back in here, and you have your f of x. Okay, so f of x comma y is going to be equal to x squared y minus y squared over 2. And then if you want, you could put some constant in there, but that should be the same answer they got. Okay, and you see it is, even though I didn't do as much craziness as they did. So what I've given you is just a formula. It works. Don't overthink it if you don't want to, but okay. So the three-dimensional one is more of a kind of a nightmare, and to do to determine if a three-dimensional vector field is conservative, you have to use this operation called the curl. Okay, so if that curl equals 0, then the thing is going to be conservative. All right. And there you see in 15.2 they're giving you another theorem, and then they're going to force you to find a potential function for a three-dimensional guy. All right, so first we need to introduce this idea of a curl, and then we'll apply it to what we're working on here with potential functions. Okay, so I'm in section 4, curl. Later on, it'll have kind of a physical significance. So it'll be about the alignment between the kind of tangent vectors and maybe some sort of other vector in a vector field. So you have tangent vectors of this particle that's moving in a circle, and maybe the vector field is kind of pushing along in the same direction, so it'll increase the kind of swirliness of this situation. You have to remember that the dot product is a measure of alignment and that kind of stuff. And then, I don't know. So anyways, and then the cross product was a measure of how much out of alignment it is. We're going to, yeah, we'll see a physical interpretation later on. I'm hoping I didn't accidentally reverse those. So let me look at, we'll be thinking about the divergence theorem and Stokes' theorem. Okay, so divergence is with flux, and we're using a dot product with n. And yeah, so curl, I'm thinking, is what I'm talking about. Okay, so let me get to the Stokes theorem. Yeah, I believe so. Okay. I believe so, but we'll see eventually. Once we get there, I'll make it more clear. But yeah, this physical interpretation of curl is kind of what I was talking about right there. Okay. Yeah, so what the heck is this curl operation that we're worried about? Regardless of how badly I'm butchering the physical interpretation. Where am I? Curl. It's going to be a cross product type operation, and okay, so regardless of the physical interpretation for now, let's just define it. So the definition, the curl of this vector field, and this is the three-dimensional. It's a three-dimensional thing. It's going to be basically, the way I think of it is in terms of kind of a determinant operation where you're taking partial derivatives of the components of f. Okay, so the components of the vector field this time will be m, n, p, and then across the top I'm going to put partial derivatives. So the curl of f will end up being, covering up the first row and the first column, partial with respect to y of p minus the partial with respect to z of n. Then we have I minus partial, so cover up the middle column, partial with respect to x of p minus the partial with respect to z of m j, and then plus the partial, so you're coming up the third one, partial with respect to x of m, partial with respect to x of n. Somebody's out there mowing my lawn. I just got done mowing my lawn. There's somebody out there mowing it. Oh my gosh. And then the partial with respect to y of m. Okay, so you just use that determinant to kind of figure it out. Let's make sure I got it right. P, N, P, Z, M, and X, M, Y. Okay, it looks good. Right. Okay, so let's find the curl of a vector field. Maybe even do the homework problem, right? So number 7, they only give you one, so let me do the one in the book. Example 7, we have vector field 2xy, x squared plus z squared, and then 2yx, or 2yz rather. So the curl then of f is going to be this determinant type thing, ijk. 2xy, x squared plus z squared, and then 2yz. And right, so the first component, cover up the first column, so it's a partial with respect to y of 2yz. So you're going to get 2z, and then minus the partial with respect to z of x squared plus z squared, so that would be 2z. So that's going to end up being 0 minus, so now you're covering up the middle column, and you're taking this times this minus this of this. So it's not really multiply, you're taking partial derivatives. So the first one with respect to x is 0. The second one with respect to z is 0, because there is no x, or in the first one there is no z in the second one. J plus, finally then, it's cover up the last column. So partial with respect to x of x squared plus z squared is 2x. Partial with respect to y of 2xy is 2x. And of course you see that in the end you get the 0 vector, which implies the vector field was conservative. Okay, so getting back to what we were talking about, we have theorem 15.2, which basically just says that. So basically it says f is conservative if and only if the curl of f is equal to the 0 vector. Okay. And then they're going to have you find a potential function for a space curve. So in example 8, or a space field, sorry, we have f is equal to 2xy, x squared plus z squared, and then 2yz. So I think that's the same field we were just dealing with, right? Sorry, I'm still listening to the guy out there doing yard work, even though I just got done doing all the yard work. All right, so anyways, what do we got to do here? So it's not going to be as easily programmable as what we did in example 6, where I gave you this formula. Instead, what I will recommend you do is basically take the integral of all 3 components and then just compare and contrast them. Okay. I sat around and thought about it last night for, is there a nice way? Is there a nice formula? I could figure. I couldn't find one, to be honest with you. If you can find one, knock yourself out, but it may not be worth it. It's not really something we're going to do a lot. So, and the examples I've seen in the book so far and in the homework, they're all pretty simple. You could just pull this off. So, with respect to x, you're going to get 2x squared over 2. Y, right? So you get x squared y, but plus this other function which has 2 variables potentially, and so the other variables will be y and z, and then same for the rest of them. Okay, so when you're integrating with respect to y, you get x squared y plus z squared y plus some function, running out of letters, h of, in this case you would have annihilated x and z materials. Then finally this last guy with respect to z would be y z squared all over 2. So 2y z squared over 2, and then plus some other function that's dependent on x and y. Okay. And you can kind of compare and contrast and see what's what, right? So this thing of x and y, if I compare it with the guy right above it, is going to probably be this guy right here, right? So, my little f of x, y, z, you just go through and kind of collect the parts, right? There's an x squared y and right there and right there. Okay, so there's going to be an x squared y. There is this z squared y right here, in right here, so I need that part. YZ squared. And then the rest of it, I'm just going to presume it's some sort of constant. So I'll put a plus C. Okay. And it seems pretty wishy-washy, but it does work for at least the ones we see in the book. I haven't gone through, like I said, and thought about it, but you know, there it is. Let's move on to divergence formula then. And again, like later on, we'll have a physical interpretation of it, which I don't want to get into it because I'm getting the divergence and the curl mixed up physically, even though I'm pretty sure curl is just swirliness and divergence is probably okay. So I'm not going to go there until we get there. So anyways, divergence of the vector field. So this one's a little easier to pull off. It's basically just the sum of the partial derivatives. Okay, so the divergence of some vector field f is going to be the partial derivative with respect to x of the first component plus the partial derivative with respect to y of the second component plus the partial derivative with respect to z of the third component, assuming it's a space field, but not a big deal. Let's see if we can do one of these. The only reason why they're hard is because they kind of give you some crazy vector fields. So number 10, the vector field x, y, z. We'll make this a video quiz. So it's kind of a silly video quiz, but maybe not. So this is number 10 in WebAssign, 15.1 video quiz. I forget which. Let me look up which guy we're on. Video quizzes, hopefully. Yeah. Okay, so I think we're on video quiz set number 9. VQ number 9. And this is the first problem in that set, 15.1. It's problem 10. Okay, so let me go ahead and do this. Right, so they give you your thingamajig. It's ln of 5x squared plus 8y squared, comma 40xy, comma ln of 8y squared plus 7z squared. And so our divergence, the divergence of f is going to be the partial derivative of this thing with respect to x. So it'd be 1 all over 5x squared plus 8y squared times the derivative of the denominator there. So that'd be with respect to x, 10x, plus the next guy with respect to y, so that's going to be 40x, plus the last guy with respect to z, that'll be 1 all over 8y squared plus 7z squared times the derivative of that denominator with respect to z, that'll be 14z. You can clean it up a little, but that's pretty much it. And we'll leave it there, and we'll see what's coming next time, I guess. You can look forward at that divergence at Stokes, the Stokes theorem and the divergence theorem, and kind of start looking at what these interpretations are. I'm sure Khan Academy probably has some good videos on those topics. They're a little better at giving physical interpretations than I am, me being more of a math person than a physical reality person. So, okay, thanks you for watching as usual, and I'll see you next time.